So this video is about chemical shift in proton NMR. What you need to know about chemical shift is essentially where you are on the x-axis is what reveals what is near the protons of interest. And in proton NMR, there's really three magic numbers that will show up again and again and again in normal spectra. The thing at 0.0 is a reference point, and that is what we call TMS. It is tetramethylsilane, and it's just something that we throw into the NMR so that we can have a reference at 0.0. 1.56 is another magic number that shows up in the NMR, and it is dissolved water in our spectrum. So that is almost always an impurity that you don't want and is not part of your stuff. And then finally, 7.26 parts per million is residual CHCl3 chloroform that's dissolved in our CdCl3 NMR solvent. So what we tend to use for taking NMR is CdCl3. There's leftover CHCl3, and that gives a line, a sharp line, right at 7.26. At 7.26 you have a sharp line. At 0.0 you should have a sharp line. And at 0.56 you'll tend to have a bump. So those are the interesting reference points in proton NMR. Now we come to certain ranges in proton NMR that are of interest. Methyl groups tend to show up down in this general region, between say 1.5 and about 0.8 or so. And that is methyl groups. Said another way, that region is pretty boring, but usually you have methyl groups in that area. Between 1 and 1.5, we tend to have things that are like CH2s bound next to a methyl group. So again, relatively boring alkyl stuff will tend to show up in that range. Around 2 to 2.5 maybe parts per million, this area right here, we tend to see things like hydrogens bound next to a carbonyl. So carbonyls, hydrogens next to a carbonyl tend to show up there. In a similar vein, if you are next to some aromatic group, that will tend to show up between 2 and 2.5 or so as well. So what you see is that in proton NMR, there are several things that can show up in a given region. So if you're immediately next to a benzene ring, you might be in the 2 to 2.5 range. So you might see overlapping regions. So the chemical shift doesn't tell you exactly what something is, it just tells you what it might be. So one thing I'll point out now is if you are further away from interesting functional groups, you tend to be toward the right. If you are bound next to interesting functional groups, you tend to be moving a little bit further left. And you'll see that as we go. The next area is one where we have several functional groups of interest. Generally between say 2.5 and like 4.5 is going to be some electronegative atom, like say an oxygen, and it'll be the hydrogens that are bound on the carbon next to the oxygen. Or maybe this would be a chlorine or a nitrogen or something like that. The more electronegative the atom, the more left you are. The more electropositive the atom, but still more electronegative than carbon, the further right you are. So nitrogens and sulfurs are down that way, oxygens and chlorines and fluorines are up to the left. Of some interest, there is a broad range between 5 and 6 that generally speaking amounts to a hydrogen that's bound directly to a double bond. So all of these hydrogens would show up generally between the 5 and 6 ranges. If you are bound directly to an aromatic ring, a benzene ring, something like that, that will tend to show up between 6 and say 8. And so hydrogens that are bound directly to aromatic rings show up between 6 and 8. There are just about 2 more interesting places to point out here, and that is a aldehyde specifically will show up right around 10. So a proton bound directly to a carbonyl, an aldehyde, that shows up around 10. And further left still, you can end up with a carboxylic acid around 12, and that is the H that's bound to the OH of a carboxylic acid. So generally speaking, this is the most useful ranges. Chemical shift tells you what you're next to. Down in the boring area, you're next to nothing. You're just a methyl at the end of a chain, or perhaps your hydrogens in the chain. Around 2 or so is a magic number. That's near a carbonyl or maybe near an aromatic ring. Around 4 or so, you're near an electronegative atom. Around 7, you're actually at a benzene ring itself. Around 10, you're at a carbonyl, you're an aldehyde proton specific. So anyhow, if you're going to remember the entire list, what you really want to think is boring around 1 to 1.5, carbonylish around 2, electronegative atoms around 4, and then double bondy stuff between 5 and 8, with the aromatic stuff closer to 7, and then aldehyde specifically at 10, acid specifically at 12. If you have these short list of numbers memorized, you're in good shape.